Alright, hello everybody. Today we are going over 1.5 for AP Chemistry, which is focusing on atomic structure and electron configuration. So today's understanding is that atoms and molecules can be identified by their electron distribution and energy. And we're going to be talking about how atoms are made up of positively charged nucleus that contain the protons and the neutrons, which are then surrounded by negatively charged electrons. The distribution of those electrons are going to determine the identity and behavior of the atoms and molecules. And then we're also going to be learning about Coulomb's law and how the forces between charged particles help explain atomic structure. First, let's go over the atomic structure. So here we have a Bohr model of calcium. We know that because it has 20 protons. And in the Bohr model, some of the ideas are the same, but we also have new information that tells us that it is a little outdated in terms of actual atomic structure in real time. So we still know that at the core of an atom is a positively charged nucleus that has protons and neutrons, and then around the nucleus are going to be your electrons that are present in the electron cloud. So in the structure of an atom, we have the attraction between the positive nucleus and the negative electrons, and the interaction between those are going to be governed by something called Coulomb's law. Coulomb's law states that the force between two charged particles depends on two things. It depends on the charge size, and it also depends on the distance. So the greater the charge, the stronger the force, and whether that is a force of attraction or repulsion is just going to be dependent on what charges those particles are. So if they are oppositely charged particles, it will be forces of attraction. If they are the same type of charge, then it will be forces of repulsion. And then the other one is distance. So the closer the particles are, the stronger the force. As they get further apart, the force are going to weaken. So in short, a large charge is going to be a much stronger pull or push, and then if you have more distance, it's going to be a weaker pull or push. And on the AP Chemistry exam, you do not have to do calculations for Coulomb's law, you just have to make qualitative comparisons using Coulombic forces with charge size and distance. So let's look at a past FRQ example in which you would use Coulomb's law to explain. So this one says the energy required to separate ions in the magnesium hydroxide crystal lattice into its individual ions is known as the lattice energy of magnesium hydroxide. As shown in the table, the lattice energy of strontium hydroxide is less than the lattice energy of magnesium hydroxide. Explain why in terms of periodic properties and Coulomb's law. Now, I know we haven't really talked about lattice energy yet, but I still think you can do this with the information you have so far. So I highlighted magnesium and strontium on the periodic table. The reason we're looking at those specifically is because the only other substance in these two compounds is going to be hydroxide. So since they're both the same, we're specifically looking at magnesium and strontium. Now, if you look at the reaction, both of them have a 2+ ion. So if we're thinking about Coulomb's law, the first thing you should think about is charge. Well, the charge is the same, so we're not using that to explain why the lattice energy of magnesium hydroxide is higher. So what we're looking at specifically is distance. This here is a Bohr model of a neutral magnesium atom. Now, if magnesium were to become an ion, a 2+ ion means it lost its two outermost electrons. So the Mg2+ ion actually looks like this. And same with the strontium ion. In a neutral atom of strontium, you had two outermost electrons in the 5th energy level, but when it became an ion, it lost the outer two. So now it only has 4 energy levels. Now, the reason I showed you this was to visualize the distance between the positively charged nucleus and the outermost electron. You can see with magnesium, the distance between the two is much smaller than the distance between the outermost electron in strontium and its nucleus. So because the distance is less in magnesium, that Coulombic force between the outermost electron and the positively charged nucleus is a lot stronger than that in strontium. So where exactly are the electrons? So we already went over the Bohr model. We know the Bohr model isn't exactly perfect. And the reason for that is a few scientists that found how electrons actually behave. So Schrödinger found that electrons behave like waves, and he used math to predict an electron's most probable location. So we don't really know where the electrons can be found exactly, but we have a sort of idea. And Heisenberg added that we can't know an electron's exact position and its speed at the same time. It's impossible. So we, again, don't really know where it is, but we have an idea of where it could be. And so these ideas formed what we call the quantum mechanical model, which uses 3D orbitals to show where electrons are probably located. And I can't show it on this video, but I did want to tell you that Minute Physics came out with an amazing video that showcases what an atom looks like in real time. So if you have a minute to go check that out, I highly recommend it. It's really intriguing, actually. Before we get into electron configuration, I wanted to address effective nuclear charge. So that is going to be the net positive charge that is experienced by valence electrons. So it's an electrostatic attraction between the electrons and the nucleus. And what it does is it takes out the shielding electrons. The shielding electrons are essentially the core electrons, so all electrons that are not the valence electrons. And conveniently, the effective nuclear charge is going to be equal to the number of valence electrons. It's not the same thing, but they are equal to each other. Here we have the phosphorus atom, and the effective nuclear charge on the phosphorus atom is going to be the net positive charge that its valence electrons experience. So in a phosphorus atom, we have 15 protons in the nucleus, which strongly attract those electrons. However, the core electrons shield the outer valence electrons from the full positive charge. So as a result, the valence electrons don't feel that full plus 15 charge. They feel a reduced plus 5 charge because we're taking out those core electrons. So now let's get into electron configuration. So when we're filling orbitals, hypothetically, in electron configuration, there are 3 rules I want you to remember. Number 1, you first need to count the number of electrons total that you have in the atom or the ion, depending on what you're doing. Next, you need to fill from the lowest energy up. So if you read the periodic table like a book, it's going to go in order from left to right, top to bottom. So it's going to go from 1s to 2s to 2p to 3s to 3p, and then when you get to 4s, you're followed by the 3d orbital, and so on and so forth. And then finally, you're going to spread out before pairing. So when you're in the p, d, or f orbitals, you have to put 1 electron in each of the orbitals before coming back and doubling up. That is known as Hund's rule. This chart is a great way to introduce electron configuration because it shows how electrons are arranged in different shells and subshells around the nucleus of an atom. So if you remember from pre-IB chemistry last year, you remember that the first energy level can only hold 2 electrons. It only has an s sublevel, that's it. And remember, in an s sublevel, it only has 1 orbital, which houses 2 electrons. And then when we get into our second energy level, that has an s sublevel and a p sublevel. Well, we know in s, it has 1 orbital or 2 electrons. And in p, it has 3 orbitals or 6 electrons. So the second energy level can hold up to 8 electrons. All right, so here we have a visual representation of the sublevels on the periodic table, S, P, D, and F. You'll notice on your periodic table, helium is normally here on the top right. but it is placed in the S sublevel over here because it wants you to realize that it is a part of S and not P. Another thing I want you to understand and realize is that the S sublevel can hold 2 electrons, and it is 2 elements wide. The P sublevel can hold up to 6 electrons, and it is 6 elements wide. And the D sublevel can hold up to 10 electrons, and it is 10 elements wide. And also works for the F sublevel, which can hold up to 14 electrons, and it is 14 elements wide. Now, when I'm talking about these sublevels, I'm referring to the energies that are associated with those electrons that are housed within those sublevels. So when we're talking about increasing energy of the sublevels, the lowest amount of energy is going to be starting with 1s. And just like I said in the previous slide, they're going to go in increasing order like you are reading the periodic table like a book. So we're starting with 1s, then we go to 2s, we go across to 2p, then we go to 3s, across to 3p, 4s, then 3d. Remember, the D sublevel is down 1 energy level. And then we go to 4p, then 5s, 4d, 5p, then 6s, then 4f, then 5d, then 6p, and then finally 7s, 5f, 6d, and 7p, which is not on here. All right, so let's go ahead and review writing out electron configuration for elements. So the first one is silicon. We know it is in period 3, and we are ending in 3p, and it is the second one, so we will be ending in 3p2. Because of Aufbau's principle, we know if we are ending in 3p2, all the other sublevels that come before that are going to be filled. So we can start at the very beginning with hydrogen at 1s2 because it is filled. Then we go to 2s2 because again it's filled. Then we're at 2p6 and then 3s2, and then we are at our final sublevel, which is 3p, and it is the second element, so it's going to be 3p2. Then moving on to calcium. Calcium is in the 4th period, and it's in the S sublevel, and it's the second one. So we know we're ending in 4s2. So we're going to fill all of the previous sublevels before that. So 1s2, 2s2, 2p6, 3s2, 3p6, and finally 4s2. And then we have tungsten, which is highlighted purple on our periodic table. We know it is ending in the 6th period, which we know D is 1 level behind. So this is actually 5D, and it is a 1, 2, 3, 4th element in that row. So we're going to be ending in 5D4. So we're going to fill everything before that. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then we go down 1 for D, so 3d10, then back to 4 for the P sublevel, 4p6. Now we're in the 5th period with 5s2. Remember, D is 1 behind, so it'd be 4d10. Then we go to 5p6. Then we are at 6s2. And remember here, right before HF is our 4F sublevel. So after 6s2 would be 4f14. And then we are finally in 5D. and it is the fourth element, so we'll be ending in 4d4. So now let's do the same thing, but with the shorthand or noble gas electron configuration. So with AP Chemistry, if it does not specifically tell you which one to use, you are more than welcome to use the shorter version. And all that is going to do is you're going to start at the noble gas before whatever element you are looking at. So if we're doing silicon, the noble gas before silicon would be neon. So we are starting with neon, which means we put neon in brackets. So Ne with brackets, and then we're starting the electron configuration from that noble gas. So after neon will be 3s2, and then we go to 3p, and it's the second element, so we'll be ending with 3p2. Then with calcium, if I look on the periodic table, the previous noble gas is going to be argon. So I'm starting with argon in brackets. So argon in brackets, and then from there I have 4s2, and that's it. And then for tungsten, I'm looking at tungsten on the periodic table, the previous noble gas will be xenon. So I'm starting with xenon in brackets. And then I start from there. So if I go look at cesium on the periodic table, that is 6s. So I have 6s2. Then I go into my 4f, and that can hold 14. And then finally I'm in 5d, and that is the fourth element, so 5d4. So obviously this way is much more efficient if you're comfortable doing that, but either way would technically work. And now I want you to do the same thing, but with some ions. So let's start with iron 2+. So to truly understand this, I want to start with the ground state electron configuration for iron, not the ion, just the neutral atom of iron. And so if we're looking at the shorthand configuration, we are starting with argon. Put that into brackets. Then we would have 4s2 and 3d, 1, 2, 3, 4, 5, 6, 3d6. Now, if I'm saying that the iron has a 2+ charge, that means it lost 2 electrons. And if something is losing electrons, we're going to assume that it is first taking the outermost electrons. Now, when we're looking at transition metals, the outermost electrons are actually the S sublevel that it filled before going into the D sublevel. So just remember, if you are doing the electron configuration for a transition metal ion, it's going to take the S sublevel that it fills before the D first. So in this case, it would lose the 2 electrons in 4s before it started taking the electrons in 3d. So the answer to this specific question would be argon in brackets, and then 3d6 because it lost the 2 electrons in 4s. Then looking at sodium, again, I'm going to start with just the electron configuration for neutral sodium. So if we're looking at sodium on the periodic table, and we want to do the electron configuration for that, we would start with neon in brackets, and then we have 3s1. Now, a positive ion means it lost 1 electron. So it lost this electron in 3s, which means it now is equal to the electron configuration of neon. But we cannot just put brackets and neon for our answer. We have to go to the previous noble gas, so that would be helium. So you can actually use helium if you really want to. Helium, and then 2s2, 2p6, or you can just write the full electron configuration, 1s2, 2s2, 2p6. And then if we're looking at the fluorine ion, this is a -1, which means it added an electron. So the electron configuration is actually going to be the same for sodium plus and fluorine minus. And that's because our ground state electron configuration for a neutral atom of fluorine would be 1s2, 2s2, 2p5, but the negative in F minus is telling us that we have one extra electron. So we're adding an electron to our electron configuration. So this 5 would now be a 6. So our electron configuration is 1s2, 2s2, 2p6. All right, and then before we move on, I want to briefly go over how to fill the orbital diagrams, specifically the sublevels with multiple orbitals like p, d, and f. So first we have the oxygen ion, O2 minus. So that means it's going to have the same electron configuration as neon because it gained 2 electrons. So if we were filling the electron orbitals, we know we're going to have a full 2p sublevel, and then everything before it is going to be filled. So our 1s is filled, our 2s is filled, and our 2p is filled. Then for sodium on the periodic table, we know we're ending in 3s and there's only 1 electron in there. So I know I'll be ending here, and then everything before it, because of the off-ball principle, will be filled. So 1s is filled, 2s is filled, 2p is filled, and then we end with our 1 electron in 3s. And then finally nitrogen. Nitrogen is ending in the 2p sublevel, and it is the 3rd electron. So if I'm looking at that, I know I will have 3 electrons in 2p, and then because of the off-ball principle, everything before it will be filled. So the electron diagram would look like this. All right, so in terms of Coulomb's law, which electron is easiest to remove? Now remember, with Coulomb's law, all of the electrons have the same charge, -1, so we're not looking at charge, we're looking at distance. The farther away from the positively charged nucleus, the less force it has. So the less force it has, the easiest it is to remove. So if we're looking at this specific Bohr model, the green highlighted electron is farthest from the nucleus, which means it's going to be the easiest to remove in terms of energy. And then to wrap up this lesson, I wanted to do one more FRQ problem. It says the first ionization energy of polonium is 812 kilojoules per mole. Is the first ionization energy of livermorium expected to be greater than, less than, or equal to that of polonium? Justify in terms of Coulomb's law. So first we have ionization energy. So the ionization energy is the minimum energy required to remove an electron. Now the 2 elements we're looking at here are PO and LV. And as you can see, PO is going to be in the 6th energy level, and LV will be in the 7th energy level. So the valence electrons in livermorium are farther away from the nucleus than they are in polonium. So if polonium has an ionization energy of 812, we know that the ionization energy of livermorium is going to be less than that because it's going to take less energy to remove those valence electrons because they're farther away. And that concludes our lesson on 1.5, atomic structure and electron configuration. If you have any questions, let me know. I am happy to help. Have a great day.